Let's talk about exponential growth and decay. So this is one of the application of the exponential function that we studied earlier. So we know this function, so say p of t is equal to p initial e to the rt. So that's the exponential function we're talking about. Now, what are these components represent? So we know that p of t represent amount at any time t, and p naught, this would represent the initial amount, meaning the amount you start with, and then r represents the rate. Now, if r is positive, meaning greater than 0, then it's an exponential growth. So we can say that we're talking about an exponential growth. And if r is negative, meaning less than 0, then we're talking about an exponential decay. So something to keep in mind when we look through examples and different scenarios. Now, also t would represent time. All right, so knowing these components, now let's take a look at our first example. So here's our first example, and let's see what we want to find. So the number of rabbits in a wildlife preserve was estimated to be continuously increasing at a rate of 12%. So we know this is R. So we know R is 12%. Now you always want to convert, so this would be 0.12. So you divide by 100 to get the decimal expression of the percentage. Now, because of the continuous increase, we know we're using the model P of t is equal to P naught e to the RT. So we know R, and we want to know how many rabbits will be in the preserve in 5 years. So that's our T. So T is 5. If the population now is 350,000. So if the population now, so that's P initial, is going to be 350,000. So we want to know what is the amount at when t is equal to 5. So P of 5 is equal to P initial, which is 350,000 e to the R, which is 0.12 times t, which is 5. And now, if you put this in a calculator, you'll see that this will give you about 637,742. So that's the number of rabbits in the preserve in 5 years. So that would be our answer to this problem. Now let's take a look at another scenario. So take a look at this one. So a culture starts with 600 bacteria. So that's how much we're starting with. So that means our P initial is equal to 600. Now, after 1 hour, the count is 7,000. So we know the amount after 1 hour, it's going to be 7,000. All right. Now, we want to find the model that will be best fit for this example. So in order for us to find that function P of t, we need to find what is R. So R is the question mark. Once we know R, we know the model. So let's go ahead and plug this in. So these two info will help us to find R. So we know the amount P of 1 is equal to 600 e to the R, we don't know, but time is 1. But we know the amount, which is 7,000. So we say 7,000 is equal to 600 e to the R, because R times 1 is just R. Now I can go ahead and divide both sides by 600 to isolate R. So we have 70 over 6 is equal to e to the R. So now 70 over 6, I can simplify that. That would give us 35 over 3 is equal to e to the R. Now to solve for R, I can take the natural log on both sides. Well, let's take natural log on both sides. We have ln of 35 over 3 is equal to ln of e to the R. Now here, using the laws of natural log, the properties, we can pull out the exponent R ln of E, and we know this is equal to 1. So we have R is equal to ln of 35 over 3. So that's our R. So what is our model? Well, our model, it's going to be as follows. So our P of T is equal to the initial amount, which for this problem is 600, e to the R, which we just found, ln of 35 over 3 times t. So now every time you have ln and e in the same question, you always want to simplify them using the laws. So I can simplify these two, and this function would simplify to just simply 600 times 35 over 3 to the power t. So t remains as an exponent. So that's our model, which will tell us the amount at any given time t. Now, that's the answer to part A. Now, what about part B? So part B, we want to know the number of bacteria after 2 hours. So we already have the model from A. Now we just need to substitute t is equal to 2. What is the number of bacteria? So for part B, plugging in t equals 2, we want to know the amount. So the amount at 2 hours, so it's going to be 600 times 35 over 3 to the power 2. Now that's good enough if you don't have a calculator, but if you want to plug this into your calculator, you'll see that the amount comes out to be 81,667 number of bacteria after 2 hours. Wow. All right, so I hope this makes sense. So that's it for this video.